Bert is a bidirectional encoder representation of transformers. It is one of the most widely used models out there for many real-world applications. For example, whenever you perform a Google search, you would have seen that Google automatically highlights the most relevant text. Now, this is powered by Bert. Bert also powers some common classification tasks like sentiment analysis, email classification to detect if the email is spam or not, and many other applications. Now in my channel, I've already created videos on transformers explaining it in depth like we are creating it from scratch. And that's what we are going to do in this video as well. Given that you know about transformers, we are going to create Bert directly from scratch. We are going to look at why Bert was needed, how it works, and why it is so powerful. So before you start with this video, make sure you at least have a little bit idea about self-attention mechanism, encoder architecture of transformers, and how the transformers work in general. And I'm really excited for this video because I've structured this video in a slightly different manner. And stick till the end because I have a bonus tip for you to speed fast your machine learning journey. We are going to discover some good stuff. So without further ado, let's get started. Before diving into what Bert is, let's understand why it was needed in the first place. Imagine that you're a part of Google's core research team back in 2018 that introduced Bert. Around this time, transformer-based models were gaining popularity. Researchers had started to realize how powerful transformers were. It is able to capture long-range dependencies in text and also parallelize training, something that was not common in NLP tasks before. Now, as someone responsible for improving the world's most used search engine, you are naturally excited and want to bring this new technology into tasks like search ranking and email classification. Up until now, all of your models are based on RNN, which processes text sequentially. But now with the advent of transformers, your horizon is expanded and you want to use it in your classification tasks. But here's the challenge in front of you. Transformers were originally designed for machine translation tasks. Their encoder-decoder architecture is excellent for understanding one language and generating another, perfect for translation. But for classification, that's a different story. In classification, you are not generating text. You are simply interpreting it and making a single prediction. So, classification type of problem require you to classify a text into a particular category, not generate text. Let's say you try to use transformers for email classification task and see what happens. You are going to pass the email body as the input to the encoder. The encoder's job is to interpret the context of the email and pass the produced output to the decoder. Decoder then can generate text autorecursively, token by token. But for classification type of problem, there is no need to generate any text. You only need to interpret the input body and classify it. So using decoder here just wastes computation and adds unnecessary complexities like masked multi-headed attention, which is not gonna be used to make a singular prediction. So you can actually get rid of the decoder here and only use encoder. And that's exactly what Bert researchers at Google did. They realized that many deep learning tasks like classification or text similarity or search ranking do not require a decoder at all. They just need a strong understanding of the input text and can make a prediction from that only. So they took the encoder block of transformers, refined it, and created Bert. The architecture of Bert is surprisingly simple. The core of Bert is just 12 transformer encoder blocks stacked on top of each other, and that's it. That's the entire main body of the model. The only difference lies in the way we pass the input and the way we process the output. Instead of passing the encoder output to the decoder, we will simply apply a prediction layer on top of the encoder's output to directly classify the input text. If you have forgotten about the encoder, then let me give you a quick refresher. The word embeddings for each word are passed as the input to encoder block, and they are then added with the positional encodings. This input is then fed to the multi-headed self-attention block. This block is responsible for generating the contextualized vector. These word embeddings are static word embeddings, which means that they are made from the general understanding of the language. Like apple can mean a technology company or can mean a fruit. Suppose initially Apple's embedding has 50% technology company properties and 50% fruit properties. Then after passing through the multi-headed attention block, the word embedding of Apple is going to shift more towards the technology company side. because the self-attention block is going to look at the context of the sentence. And in this, the Apple is used with iPhone, which means that we are talking about the technology company. So self-attention block is going to generate a new embedding representation for Apple that will align more with the technology company side. Not just this, as there are multiple heads of self-attention block, each head is going to process and capture different relationship of Apple with the other words in the sentence. For example, it can capture that the Apple and iPhone go together and is a single entity, and it can also associate that there is an ongoing mega offer on the Apple iPhone. For each input word embedding, the multi-headed retention is going to produce a contextualized vector. These contextualized vectors are then passed to add a norm layer for the stability of the training of the model, and then feed forward network. This feed forward network is used to add some non-linearity in the model, as well as add some more model parameters so that the model can capture complex pattern in the data. And finally, we can say that encoder's output is a contextualized representation for every word. For each input word embedding, the encoder is going to generate a contextualized vector of the same size. This contextualized vector will not only have the general property of that word, but also understand the relevant context of the sentence and the associations and dependencies among the entities. In Bert, the input is processed by 12 such encoder blocks. Now, question in front of us is, how do we convert these contextualized vector into a classification? How do we use this to classify if this is a spam or not? So if this is our Bert model with 12 encoder blocks, how do we process this input so that we can classify this text as a spam or not? One simple technique could be that we perform an average of all these embeddings and generate an average embedding. This average embedding can then be passed to a linear plus softmax layer, which can classify if it is a spam or not. This linear plus softmax layer is represented by this formula. It is softmax of W of E average plus B. Basically, we multiply the output with the weight matrix of this layer, add some bias and pass it on the softmax. Softmax is going to convert it into probabilities. As we are performing a binary classification, the output of this softmax layer will be a singular value, and this value will lie between 0 to 1. If this value is greater than 0.5, then we can classify it as spam. If the value is less than 0.5, then we can classify it as not spam. So this is one of the way to use transformer encoder blocks for classification task. This approach will work fine, but if you carefully observe this, then it has a problem. And the problem is that we are averaging all of the embeddings. Every embedding is given equal weightage. And this can reduce the accuracy of the model, because it means that we will also add a lot of noise, because it is possible that some of the word embeddings might not contribute to the spam detection. As we are giving equal weightage to everything, they will also be added. And this way we are not dynamically focusing on the relevant words. For example, the word mega offer can be the strongest contributor in the spam detection, but they are getting the same weightage as the rest of the words. For better accuracy, what we would like to do is we would like to give some higher weightage to the words that contribute most for that specific task, and lower weightage for the words that contributes lesser. And if you think carefully, you already know a way to achieve this. Isn't this our self-attention operation itself? That's what self-attention does, right? It captures the similarity, and based on this similarity, the weightage of the relevant context is decided. For example, if there is a strong dependency between the word Apple and iPhone, then to generate the new contextualized representation for Apple, I will be adding a higher weightage of iPhone and lower weightage of words like offer and mega. And we just want to do the similar thing over here, but for the spam and not spam classification. And that's where the researchers at Google came up with a simple yet powerful idea. Instead of using this pooling layer, what if we add a special CLS token that will capture the relevant context dynamically? And we only use the output for the CLS token to make our spam or not spam prediction. So instead of blindly averaging the output, we delegate this responsibility to this CLS vector. This CLS vector is known as classification token. and we directly use the output corresponding to the CLS for the classification task. We train the model in such a way that this CLS vector learns to absorb relevant context from the input that matters most for the classification. This token has its own word embedding just like any other words in the sentence, and it is always placed at the very beginning of the input sequence. This token is treated just like any other word. It is going to participate in all encoder operations, that is self-attention, add norm and feed forward layers. And because it is interacting with the other words in the self-attention operation, it will absorb the relevant context in itself. While generating the new contextualized representation for CLS, it can decide which words are more relevant for the classification and absorbs those words' context more and ignore the other words. In a way, we can say that this CLS token might be a summary-like representation of the input, because this summary-like representation can be used for spam and not spam classification. And this way, instead of blindly using the average pooling layer, we are dynamically absorbing the relevant context. It's smart move, right? I know you might be wondering that, Jay, how does the CLS know which relevant context to absorb? Initially it is neutral, right? So how does it know which context is more relevant? We will talk about this later in this video when we are discussing the training of the model. We will train the model in such a way that we will force the model to store the summary-like representation in this CLS output. But I hope you are able to understand the role of CLS token and its use. Let's move forward with our discussion. So far, we have focused entirely on the output of the CLS token. But what about the output produced from the other words in the sentence? Are we going to completely discard it and not use it at all? Well, the answer depends on the type of problem we are solving. There are two broad categories of classification problems. One is sentence level classification, where we interpret the entire sentence and classify it in a particular category, like spam, not spam detection, sentiment analysis, movie rating prediction, etc. For these kinds of problem, the output of CLS token is all you need. The CLS vector captures the overall context, so you can safely ignore the outputs of the other words. But if you are solving token level classification problems like named entity recognition or parts of speech tagging, then CLS token output is not helpful, because we aren't interested in the summary, but we want to make prediction for every single word. Let me give you an example of named entity recognition problem. In this problem, you are given an input sentence and you want to classify what each word belongs to. Like Google is an organization, California is a location. So you want to capture the informations like names of the organization, people, date, locations, etc. So for this kind of problem, the output produced by CLS is not going to be useful, because this is not sentence level classification, but it is a token level classification. In this kind of problem, we simply ignore the CLS output and we simply use the output produced by the words of the input. We apply a linear and softmax layer on it, which will classify it in a particular category. So this is how the output layer changes in Bert. If you want to do sentence level classification, then simply use the CLS output and ignore the output produced by the other words. But if you want to do token level classification, then ignore the CLS output and use the output produced by the other words. So I hope this is clear. I think we are ready to discuss how the training works in Bert. There were two main reasons for creating the Bert model. One was we wanted to use transformers for classification task. And second was to make a general purpose pre-trained model available so that anyone can later fine-tune it for their specific task. And we wanted to use transfer learning. Before the advent of transformers, the transfer learning in NLP task was very challenging because the RNN based models were not supporting it. But now, as we had transformers for NLP tasks, we wanted to utilize its transfer learning capabilities. Transfer learning can be described with something like this. You train the Bert once on a large corpus of data. The purpose of this training is to help Bert learn a general understanding of the language. Things like grammar, sentence structure, meaning, relationship between words, and how the context changes the meaning. Here we are not fine-tuning Bert on a specific task like spam or not spam detection. We are just allowing the Bert to develop a general understanding of the language. Once Bert knows how to read, interpret, and understand language, we can then use it for classification tasks by later fine-tuning it. Fine-tuning of a pre-trained model will be done on a specific task on which we want to use the Bert. Because the Bert already knows to interpret the language well in the pre-trained phase, the fine-tuning will require very little amount of data, computation, and time. And that's the best part about fine-tuning. Fine-tuning takes very little time and data. If you're using a GPU or a TPU, fine-tuning can take as little as 30 minutes to a few hours. That is why Bert is so powerful. Someone else has already done the heavy lifting of pre-training it. You just have to give it a little bit of polish to make it relevant for your specific task. That is why Bert is pre-trained open source model which is available out of the box. Anyone can download the pre-trained model, fine-tune it on a specific task, and then can use it. But how do we pre-train this Bert? What exactly do we do in that? Let's take a deep dive into it. To pre-train the Bert model, there are a couple of things that we need to keep in mind. First of all, we need to train it in such a way that we can use this CLS output for sentence level classification. And second is, we also want to use the output from the individual words for token level classification. So in short, one model should be able to understand language deeply and can handle different types of classification problems. For this, first we need a large amount of data. And second is, we need to figure out a task on which we will train it. We need to choose a task in a way that the model can understand the general language. And also keep in mind, as we are using a large data set, we don't want to manually label millions of sentences. That would be painfully time consuming. Instead, we want to use a raw, unlabeled text like books, articles, Wikipedia, and somehow design our task in such a way that our model can learn general language. So what kind of task can we choose? The traditional NLP models were usually trained to predict next word for a given few input words. This is a standard language modeling task, and it is great because you don't have to label any training data. You can pick up any sentence and just ask the model to predict the next word. But this task is not ideal for Bert. Remember, Bert doesn't have decoder, so it cannot generate text. It cannot generate the last word. But we can modify this kind of task and redefine the problem to ask Bert to predict a missing word in the sentence. What if we randomly drop certain words in the sentence and replace them with some mask token? And we ask Bert model to make the prediction for this token. This way, we set an expectation from the model that, hey, I'm going to use the output produced by these words for my prediction. So you better make sure that you train yourself in such a way that I can use the word outputs for my downstream tasks. This kind of training will later help us in tasks like named entity recognition. And as we are asking the model to predict the missing word, the model has to look both forward and backward to predict the word at this position. And it is perfect for our Bert model. Do you know the full form of Bert? It is Bidirectional Encoder Representation of Transformers. Notice the word bidirectional here, which means that it looks at both the forward as well as the backward direction. How does it look at both the directions? Simply by using this self-attention. Self-attention processes all the words parallelly, which means that at any given point of time, the word at this position has access to all the words appearing later and before it. So it is looking at both the directions. This kind of modeling is known as masked language modeling. Here's how it works step by step. We first randomly drop 15% of the words from the training data set and replace it with mask keyword. Assume that our training batch size has only 2 sentences. We drop 15% of the words from each sentence randomly, not in the batch, from each sentence randomly, and replace it with a mask token. This masked token is another special token in our Bert vocabulary, just like the CLS token. It also has its own word embedding, and it is also going to participate in all of the Bert operations like self-attention, feed forward, add and non, all of them. As we have passed 2 sentences and word embedding for each of the word in the sentence, the output from the Bert is going to be of the same size as the input. We will get a new contextualized representation for every single word in our batch size. Now we only use the contextualized vectors for the mask token and pass it on linear and softmax operation. This linear and softmax layer is going to produce an output of the same size as the size of the vocabulary. Let's say if our vocabulary has 100,000 words, then the output from this layer is going to be 100,000 dimensional vector. And as the output is coming from the softmax layer, all the values are going to act as probabilities. We pick the highest probability and the index corresponding to that probability will be our word prediction. For our masked language modeling in pre-training, we simply ignore the output produced by the other tokens. We only use the output produced from the mask tokens, pass it to a linear and softmax layer, produce a prediction, and then we compare this predicted word with the actual word that should have been there in this position. From this comparison, we compute a loss. So if the loss correspond to this token is L1 and this token is L2, then we simply perform the average of L1 and L2 for this batch of data. This will be our final loss. We will use this loss to update the model weight parameters via backpropagation. Also, as we are randomly masking the positions, throughout the training, the model will get enough opportunities to make predictions at every positions except the CLS position. The CLS token is never going to be masked, so we will never compute a loss corresponding to CLS token and will simply ignore its output. But I know you might be wondering, if we are not masking it, how do we train the model to use CLS token for sentence level classification? And the answer is, to train the model to use CLS token, we require a different training altogether. We need to choose a task on which we can train the model to use CLS token for sentence level classification and ignore the output produced by these tokens. So this requires a separate training altogether. So pre-training in Bert happens in two phases. One of the phase is masked language modeling, but there is another phase on which we need to train the Bert. But before I tell you that, I want to encourage you to think for yourself. What kind of task we can choose so that we can train Bert for sentence level classification. Also keep in mind that we don't want to manually label the dataset like for spam and not spam detection or sentiment analysis. We want to use general text available from books, internet, Wikipedia, online blogs, etc. Can we choose this kind of problem where we take two consecutive sentences and predict if the next sentence naturally follows the first one or not? In this example, these two sentences are valid consecutive sentences, while these two sentences are not valid consecutive sentences. This is a binary classification problem where the output can only be true or false. And this kind of problem will not require us to manually label dataset. We can use general text from anywhere. All we have to do is we have to pick up two consecutive sentences from our text corpus and keep 50% of those pairs as is, which means that these pairs will correspond to is next equals true. While for the other 50% of the pairs, we randomly swap the second sentence. As the swapping is random, we can safely assume that now these pairs will not be following a natural order, and these will correspond to is next false category. This kind of training is known as next sentence prediction training. And here's how it works. We pass the training data that we prepared to Bert model without any masking and ask Bert to produce outputs for each token. We then only use the CLS token output for the final prediction and ignore the output produced by the other tokens. We pass this CLS output to a linear plus softmax layer, which will act as a binary classifier. This classifier will predict if the second sentence follows the first sentence or not. We then compute the loss corresponding to this. So if the loss for this token is L1 and if the loss for this token is L2, then we simply average L1 and L2. And this will be our final loss, which we will use to update the model parameters in the backpropagation. Now, how does this training help? This training forces the model to understand the sentence level context, and it also forces the model to use the CLS for the final prediction. Because we are only using the CLS for this kind of classification, the model will eventually learn that this token should have the relevant information for these kinds of classification problem. And as this problem requires the overall sentence knowledge to determine if the second sentence follows the first or not, the model will learn to compute the summarized representation in the CLS token. And that's how it works. Pre-training works in two phases. One is masked language modeling, second is next sentence prediction. But before we move forward, I want to highlight another problem in this. If you carefully observe this next sentence prediction, you can raise this question that, Jay, how does model know which is the first sentence and which is the second sentence? If we club all the words of both the sentences in a single data point, then what is the differentiator through which the model will understand that this is the first sentence and this is the second sentence? The model needs a clear differentiation, right? Otherwise, how can it make accurate predictions? And that's a good catch. We somehow have to define a boundary and explicitly tell the model that, hey, this is my first sentence and this is my second sentence. To solve this, we need to provide some input to the model that can act as this differentiator. And that is why the input is slightly different in Bert than in vanilla transformers. We add two more things in the input. First is segment encoding, and second is another special token known as SAP token. Now, what are these things? Let's look at them one by one. We know that the input to word is word embeddings plus positional encodings. Along with this input, what if we add another segment encoding in the input? What is this segment encoding? It simply tells the model which token belongs to which segment. We are adding segment encoding of 0 for the words in the first sentence, while we are adding the segment encoding of 1 to all the words in the second sentence. This segment encoding of 0 is very simple representation where all the values are equal to 0, while the segment encoding of 1 is a vector where all the values are 1. The size of these segment encoding is same as the size of the word embeddings or positional encodings. We keep the size of word embedding, positional encoding and segment encoding same so that we can perform an element-wise addition between them. So SE0 is a vector of all zeros of the size same as the size of the word embedding, and SE1 is a vector where all the values are 1 and its size is same as the size of the word embedding. And we simply perform an element-wise addition between all these three types of embeddings and pass it as the input to Bert. Now you might ask me, Jay, how will the model interpret the segment information from this segment embedding? The moment we add some value to the original word embeddings, their position in the multidimensional space is going to change. Imagine it like this. Let's say the words in the first sentence are marked by blue and the second sentence are marked by green. After we add the segment encoding, the words in the second sentence will change their position like this. So the model will be able to separately interpret them in different clusters. This way, self-attention will know if the word belongs to first segment or the second segment. Also note that the original word embedding properties are not going to change. Model will still be able to interpret the properties of the word from the word embeddings. How does this happen? Because the segment encodings are orthogonal to the word embeddings, just like how positional encodings are also orthogonal to the word embeddings, which means that despite we perform an element-wise addition between all these three, they do not interfere with each other. The model can separately interpret all these three kinds of information. If you don't understand what I just said and you're curious to know more about it, then you can check out my positional encoding video. In that, I have explained this orthogonality properly. But for now, understand that in every input to Bert, we always add segment encoding. And as we are using multiple heads of attention, some of the attention heads might capture the relationship between words within the same segment, while some other attention heads might capture cross-segment dependencies. And with this, the model will learn the sentence context and the relationship between the two sentences, which will eventually help it understand if the second sentence naturally follows the first one or not. But this segment encoding is just not enough. We also provide some additional support by adding a special SEP token between the sentences. We place the SEP token at the end of each sentence, which acts as a clear, explicit boundary marker. And the input format will change to something like this. There is a typo here. This should be position embedding 6. This should be position embedding 7. This should be 8, 9, and 10. Notice how we add SEP token embedding at the end of the segment. This SEP token is another special token in the Bert vocabulary, just like the CLS token and the mask token. It is also going to participate in all encoder operations, and Bert will create a contextual representation for it. Just that we do not use this contextual representation for SEP token in any way. We simply just ignore it. Because the purpose of this SEP token is just to explicitly mark the boundary. We don't want to use its output. Over the time, Bert will see that the SEP token consistently appears at the end of the segment and learn to associate with the sentence boundary. So with both segment encoding and SEP token, Bert now has enough clues to differentiate between two sentences. Now that we have explored both pre-training tasks, that is masked language modeling and next sentence prediction, you might wonder, Jay, does it mean that the model needs to be trained on these tasks one after another? Wouldn't that double the training time? And that's a great question. The answer is no, we don't have to train them separately. Instead, we combine both the tasks into a single training process. But how do we do that? Here's how. We structure the input in this format. The first token is always a CLS token. We add SEP token at the end of each segment, and we also add segment encodings to the word embeddings. Now this will help us with the next sentence prediction problem. But can we also combine the masked language modeling problem here? Why not? What if we simply drop some random words and replace them with the masked tokens? This way we are combining both the input formats and asking the model to make predictions for both of them at the same time. This entire input will pass through Bert, and Bert will generate new contextual embeddings for all of them. We then use the mask tokens to predict the missing word, while we use the CLS token to perform the binary classification and check if the next sentence follows the first one or not. Both of these linear and softmax layers are different from each other. This one is a binary classifier, while this one predicts the word at a missing place. And then we compute the loss at the masked positions and average them. So in blue, I will write the loss for MLM problem. And we separately compute the loss for the CLS positions, and in green, I'm writing the loss for the next sentence prediction problem. We simply add the loss for both of these problems, and this becomes our overall loss, which is then used to update the model weight parameters in backpropagation. This combined training strategy is both smart and powerful, and with a single dataset, we can complete the entire pre-training of Bert. And this completes our discussion on Bert. We have covered a lot of things, so let's take a quick summary before we end this video. Bert is designed for classification type of problem. It is not suitable for text generation because it doesn't have a decoder. For text generation, we use models like GPT, which I will cover in the upcoming videos. Bert architecture is just stack of transformer encoder blocks, nothing fancy. The real difference lies in the input format and the output layers. The output layer for Bert changes depending on the type of classification problem. For sentence level classification, we use the output from CLS, while for token level classification, we use the output from the words. The output from the CLS token acts as a summarized context, providing the required context needed for the sentence classification. Bert uses transfer learning, which means it is a pre-trained open source model. In most cases, we simply use this pre-trained model, fine-tune it on our specific task, and use it. Fine-tuning requires very little data and time because most of the training is already done before. Pre-training is done by combining two tasks, that is masked language modeling and next sentence prediction. For the pre-training of the Bert, we have to pass the sentence in this format, while the sum of the tokens will be dropped and will be masked. We also add segment encoding along with the word embeddings. Now something super important to note here. As we are passing the input in this format in training, we cannot change this input format during inference time. We have to use this format for inference time as well. Just that for inference time, we will not be masking anything, but we will be simply adding the SEP token, we will be adding the CLS token, and we'll be adding this segment encoding. And this will be our input format during inference time. So if you want to use Bert model for email classification, then your input should be formatted like this. If your input body do not have multiple segments and only has one segment, then you can just use one segment for this. You will not be adding this segment encoding for the next sentence, but you will only use it for the first sentence. and you will also use the sep token at the end even though you do not have the second sentence. Why this? Because if we change the input format from training to testing, the model will be confused. The model is used to seeing sep token at the end of the segment. So if you do not pass this sep token, then the model will not be able to predict accurately. You can even pass multiple segments, more than 2 segments, and separate each segment with sep token and add different segment encodings for the different segments. It all depends on the type of problem that we are solving. Now this completes our entire theoretical discussion of Bert. As I promised at the beginning of the video, here's the bonus tip for you to enhance your machine learning journey. The way I have structured this video is I wanted to give you the whys and hows of the concept, like why this model was needed, what was the thought process behind its creation, things like that. I wanted to explain it like we're creating it ourselves from scratch. Now, I want you to use AI tools like ChatGPT and DeepSeek R1 to enhance your understanding. If you have any specific question, then ask it to ChatGPT. They give you a very tailored response for specific questions. The only problem with these tools is that if you ask it a very general question like what is Bert, then they are going to throw a lot of technical jargons at you. It will directly start to explain you that Bert uses CLS token, SCP token, mask token, and how the training works. But it will fail to tell you why all these things were needed in the first place, why we couldn't have taken some other approach. And when you know the whys of the model, you understand it thoroughly and you remember it. You won't have to go back to this concept and look at your notes again because it will be ingrained in your mind. And that's what I want you to do. Use ChatGPT as your companion. Use my videos to understand the whys and hows of it. But if you want to dive deeper and know more about the whats, then use tools like ChatGPT. Now for Bert, I have already created a template that you can use to ask better questions to ChatGPT. Make sure you provide the context to ChatGPT that this is your current understanding and this is what you don't understand and this is what you want to understand, and see how well its responses are. I'm also giving you some questions that you can ask right away after this video to ChatGPT to enhance your understanding on Bert. There are some things that I have not covered in this video, otherwise this video would have been very long. I want you to ask these questions to ChatGPT because it can explain you very well. You don't need me in that. So that's it for this video. I hope you found this valuable. Please let me know your feedback down in the description if you found value from this video or not, or if you like this kind of structure. Subscribe to this channel to never miss an update. Like this video if you found this valuable. Your support is very important to me. And that's it for this video. I will see you in the next one.